process, and this also has a marginal as a power function distribution. This process is given in the equation number 3. Xn is equal to maximum of xn minus 1 alpha by alpha minus delta un to the power 1 by delta. So we will be needing the Kundu PFD process and AM PFD process for moving further. So now having in transformation of the Kundu PFD process. So it is an increasing monotone transformation of the Kundu PFD process. So now based on that idea, we are introducing some other GE process, which this also has a generalized exponential distribution, but it is a stationary as well as Markov process. So the yn is equal to maximum of these terms, and here xn star is AMPFD process, and un is uniform random variable, uniform 0 1 random variable, and it also has a generalized exponential distribution as a marginal distribution with parameter alpha. And we can equivalently rewrite it in the following form: yn star is equal to minus log of 1 minus xn star, where xn star denotes the AMPFD process. So we can see that AMGE process is an increasing monotonic transformation of the AMPFD process. So now going to the viable processes. So in Kundu 2023 paper, this process was described. This is a stationary process, and Zn is equal to minimum of these two terms, and this Zn follows a viable distribution with gamma and alpha plus beta parameters. So this is a stationary process. Additionally, this process we saw that can be obtained by a marginal transformation of the Kundu PFD process discussed in this paper, and with this transformation. So clearly, Kundu viable process is decreasing monotone transformation of the Kundu PFD process. Now, based on that idea, we are introducing the AM viable process, and with the very different structure from that structure. So here we are taking En be the sequence of standard exponential random variables. So the AM viable process is defined as a Markov chain. Zn star is with the transition given in the equation number 7. That is Zn star is equal to minimum of these two terms, where Zn is AM viable process, and Zn has a viable distribution with gamma and alpha distribution. So, and this is a stationary Markov process, and this process can also be obtained or expressed in the following equivalent form where xn star is AMPFD process. So now, after discussing some definition and some stochastic properties of the four processes, now going to the statistical inference part of this. So for all the process I have discussed, we don't have a closed form of the joint densities. So we can't use the usual standard like estimation methods, such as method of likelihood estimation or Bayesian method. So we have used some modified method of movements for all the process. For the Kundu GE process, we have used the modified method of movement approach based on the following two statistics. Kundu GE process has two parameters, alpha and beta. So for that, we use the two statistics, y bar and py. To py, we are calling it as a fluctuation probability. And as yi is follow generalized exponential, so expectation of y bar we have readily available. And for the expectation of py, that is, since the Kundu GE process is monotone increasing transformation of the Kundu PFD process, we use its non-fluctuation probability. So after some, like in the previous work, we have described it that after some tedious calculations, we have probability of x1 less than x2 as this. And this can be equal to the probability y1 less than y2. So after equating each statistics to expectation and solving else the estimates of the Kundu GE process, that this has two cases, alpha greater than beta and alpha less than beta. And here in this we have the estimates of the Kundu GE process, and they are all consistent and asymptotically normal. Now going to the estimates of the sir, how much time I have remaining?
You have 4 more minutes.
Okay, sir. Thank you, sir.
Sorry,
so
3 more minutes. Sorry.
Okay, sir. So going to the AMGE process with a similar procedure, and we have used the same two statistics, but although they are following some different distribution, so we have this probability of x1 less than x2, and by similar approach, we have the following estimates of the parameters of the AMGE process, alpha and delta. So where py star is empirical fluctuation probability. Now going to the estimation of the viable processes. Firstly, for the Kundu viable process, if Kundu viable process, we have three parameters: alpha, beta, and gamma. So we are using the three six M1, M2, and PZ, and we have its expectation readily available. So for alpha beta, for the Kundu viable process, we have estimated parameters alpha less than beta. Also, we have estimated parameters. So we have three parameters: alpha, delta, and gamma. So we estimate these parameters using the following three movement equations: M1, M2, and PZ. We are using three statistics, and we estimate gamma by solving the following equation numerically. And after we have the gamma, then we have alpha and delta. So we have estimated all the parameters for all the four processes. Now going to the simulation part, we have simulated simple paths for the each model across various lengths with various parameter combination. For the GE process, Kundu GE process, AM GE process with various different combination. For the viable process, various different combination. And we have from the Kundu, this is the are simulation graphs of the Kundu G process. These graphs shows that as we are increasing the sample size, the estimates are converging to the true parameter value. And we have some tables I have not included for the time constraint. The standard errors are also decreasing as we are increasing the sample size. This was for the Kundu GE process. This is for the AMGE process, and this is for the Kundu viable process, and this is for the AM viable process. For all the four processes, the movement estimates are converging to its true value, and standard errors are decreasing as we are increasing the sample size. So now demonstration of the real life data. For the GE process, I've used the Apple stock price of January to December 2022. It has 251 observation, and I have estimated the parameters using the method of movement estimates. First table is Kundu GE process. The other table is AMGE process. The important point is that goodness of it was assessed by the MSC between observed and simulated paths. So I've repeated it 5,000 times, and we have calculated the mean of the MSCs, the MMSC.
Sachin
And
Sasdeva,
yes, sir.
try to conclude it.
Okay, sir. So that we have used the mean of the mean square errors. So the AMGE process showed a slightly lower MMSC than the Kundu GE, suggesting a better fit. However, due to the structural differences, such simulation-based comparison are not fully reliable without formal goodness of fit tools. So we this inconclusiveness highlights the need for the developing appropriate goodness of fit tools for such process. Similarly, for the viable process, I have used the Wipro stock price data for the 2000 year, and we have the MMSC for both the data. So here MMSC was same almost. So again, we emphasize the need for the dedicated goodness of it. So we have fitted the data, but we are
Yes.
not able to decide. And so these are some generalization that we can we can generalize it to the proportional reverse hazard processes. And so these are the that I have used.
Well, okay, right. Very good. Sir,
Thank you.
Professor Dilip Ghosh and Professor Kanchan Jain.
It was very good presentation, but you want to show that the method of Kundu G and Weibull is non-Markovian.
Yes, sir.
And did you publish this paper?
Yes, sir.
You published?
Yes, sir.
Showing that Kundu's method is not Markovian.
Yes, sir.
Okay. Now my question is that when we showed the two tables, from table I saw that in case of Kundu's, alpha, beta, SMSE is less than your methods.
No, sir.
Both for Weibull and for G.
No, sir. My is little less. Our one.
Just show me the table.
So this is for the G.
See, alpha, beta is in case of Kundu G process is less than your process, na?
Sir, alpha, beta, and they are parameters, so they can be anything.
Achha, they can be anything. Then SMSC is less here compared to your.
Yes,
only
sir.
MMSC is little bit, just 0.003. It is negligible. It is.
Yes, sir. Sir, SMSE means standard error of the mean square errors. So means we have calculated the mean square error, 5,000 mean square error, and I have taken the standard deviation of the mean square error.
Let's see the difference, only
Yeah.
0.003.
Yes, sir. That is why, sir. Like,
and this cannot be say that is a conclusion.
yes, sir.
On this data, it may be like that. For other data, it may not true.
Yes, it may not be true, sir. Yes, sir.
But whereas SMSC, square mean of square error, is less than your method.
Yes, sir.
SMSC.
Yes, sir.
So this cannot be predicted that that is not Markovian or this and that.
So that's why, no, sir. That's why if I've written it there, the AMGE process showed a slightly lower MMSC than the Kundu GE process. However, due to their structural differences, such simulation-based comparison like MMSC, SMSC are not fully reliable without formal goodness of it tools. Sir, but currently no better alternative available to us.
Okay, thank you.
Make your answer precise. Very good.
Okay. What was the full form of AM?
It is based on like two authors like Arnold and Manjunath, sir.
Manjunath.
Yes.
Okay. And when you were showing the transformations,
Yes, ma'am.
were they same in two situations? Minus log of that one minus.
No, ma'am. They're different. One is increasing transformation, and that one some parameters are also different. It's gamma is coming. There's no gamma in GE processes.
Okay.
Yes, ma'am.
And okay, I think Professor Ghosh has asked you the same question, which I was thinking. So that's already answered. And another thing, like fluctuation probabilities.
Yes, ma'am.
Can you go back to that slide? Just for one moment. This next one. This one. Here you say probability of Y1 less than Y2 is same as probability of X1 less than X2. Why are these two probabilities same?
Ma'am, I have because this is YN is in an increasing monotone transformation of the Kondo PFD process. So when I calculated, so this all these logs and all get cancelled.
Okay.
So probability is same.
And another transformation was not similar, star 1.
This,
Yes.
yes, ma'am. This is similar for the
This is
GE process.
similar, no?
Yes, ma'am. For the viable, it is some other parameters are coming.
But you are borrowing those probabilities from someone else.
No, our work only, our previous work.
You had calculated those.
Yes, ma'am.
Okay. Thank you.
Thank you.
Well, thank you, Sachin Sachdeva. You can wind up the screen. And the next presenter is Agniva Das.
Good evening, sir.
Sir, we are having only half an hour and two presenters, two contestants. Yes.
My screen visible, sir?
Yes, start.
Yes, sir. So, first of all, a very good evening to the esteemed judges, respected professors, students, scholars, and last but not least, the organizers of WSTA 2025. I am Agniva Das, and it is my privilege to present our work titled Robust Change Point Detection via Penalized Autoregressive Models and Fourier Probabilistic Neural Networks. This research addresses a long-standing challenge in statistical time series analysis, the reliable detection of structural changes in the presence of autocorrelated noise and transient outliers. Our framework basically combines a statistically grounded segmentation method with a compact interpretable neural component. And we seek to bridge a classical statistical modeling with modern machine learning techniques. I'll begin by briefly outlining the motivation and objectives before moving into the methodological core. Quick note, this work has been co-authored with my PhD guy, Professor K. Muralidharan at MSU Baroda, while I was a research scholar there. And this has been submitted for review and subsequent publication to the JISPS in Springer. The contact details will be given in the last slide. Now, a quick overview. We'll talk a bit about the motivation and objectives. Then we get into the research methodology. We'll discuss some of the results and the conclusions and future scope related to the work. Now, firstly, change point detection is central across various domains. We have finance, geophysics, genomics. Existing methods often assume white noise and fail with autocorrelated noise and dense outliers, and they lead to a high number of false positives. So, as you can see, because of this, there are many papers in literature that have addressed this issue. And so what are our objectives here? So firstly, we want to propose a hybrid two-phase change point detection framework. And we want to address the simultaneous presence of autocorrelated noise and a high dense, concentration of outliers within that data set. And to accurately distinguish between sustained shifts and recoiled deviation. So what happens is during change point analysis, it may happen that the mean has changed, but it has sustained. So, and in some cases, the mean, although it changes for a few observations or for a single observation, it recoils back to its original mean. So, in certain cases, in certain applications, it might be important to know which shift will stay or sustain and which shift will recoil in the subsequent time points. And this is an overview of our research methodology. So first, we have a training phase where when we train a signal-based model which signals the change point, whether or not a certain given point is a change point or not. In the training phase 2, we train a Fourier probabilistic neural network only on the obtained change points from the previous phase. And on the basis of that, we basically build a classification algorithm, and we classify whether or not that particular observation is a sustained shift or a recoil shift. And in phase 3, we simply test whether or not our model is classifying to the extent that we want. And we are also comparing models based on the testing data, based on our testing results. We'll be comparing the DCAPS method, the method that we are using, which is nothing but short for detecting changes in autocorrelated and fluctuating signals. And similarly, we'll be comparing it with BOCD, or the Bayesian online change point detection, the Age SMUC, or heterogeneous simultaneous multi-scale change point estimator, or the ENVCTB, or the which is the envelope change point technique, which is used specifically for environmental applications, and the PELT, or the pruned exact linear time algorithm. These are some of the more popular state-of-the-art change point detection techniques that are used, and we have used these as a benchmark for comparison with our framework. So next, this is